Thanks. Thank you. Thanks for the invitation. Yeah, so I'll give both an overview of what it means to derandomize space-bounded computation and also survey some recent results. Some I will only mention, and some will be we'll see more details about. Okay, but let's start from the basics. Yeah, I'm sure I don't need to convince you much, but I'll say it anyway, that randomness is very valuable in computation, right? We use it in algorithms, in crypto. For crypto, it's essential, actually, for distributed computing, for medical trials, for protocols, all over the place. It is often essential, for example, for crypto, which I mentioned, for property testing and for other uses. But regardless, I mean, sometimes it's not essential, but regardless, it's incredibly useful. It's often faster and simpler in practice, and sometimes that's all we have. For example, for polynomial identity testing or for approximating the number of perfect matchings, we have efficient randomized algorithms, but no efficient deterministic ones. And whenever randomness is used, we assume a perfect source of randomness. And we want the randomness to be as pure as possible, but it's notoriously hard to come by. And we indeed need to treat it as a resource. So the same way as faster algorithms are better than slower ones, and memory efficient algorithms are better than ones that consume a lot of memory, in the same way algorithms that use few or no randomness, but are still efficient, are better than algorithms that use a lot of randomness, right? It's a resource. Yeah, by the way, stop me if you have any questions, of course. So in the time-bounded regime, meaning randomized algorithms that run in polynomial time, I saw you had a talk by Lige today, right?
Yep. Yes.
Yeah. Okay. So I believe you talked about the fact that we believe that every randomized algorithm that runs in time t can be simulated, even in a black box spanner, which is cool, in time t to the c, where c is some constant. Namely, we believe that p equals bpp, and we believe it since it's true, assuming circuit lower bounds that we believe to be true. And there's been a recent progress, which I'm sure you heard about, on both what the C should be and also on the hardness assumptions. But the gist of it is that we can't make unconditional progress in time-bounded algorithms without breaking lower bounds. But in the space-bounded regime, we don't have any barriers, seemingly. And here too, we believe that any space-bounded randomized algorithm can be derandomized, meaning it can be simulated deterministically with only a constant factor overhead in space. Okay, and namely this is called the BPL versus L question, and I'm going to define it formally. And this also, in fact, follows from circuit lower bounds. Namely, we know that if there exists a language in linear space that requires exponential size circuits, then BPL equals L. But there are many exciting unconditional partial results. And what do I mean by partial results? Either partial derandomization of the entire BPL, or optimal or near optimal derandomization of subclasses of BPL. Okay?
Sorry, but I'm not very sure about the super lower bound implies BPL equals L. And can you show the reference for me?
Yes, it's Van Malkebeek, and can you send me an email and I'll send the paper to you? It's in the appendix. It's an appendix of I think it's called Graph Non-Isomorphism has showed. I don't remember that on top of my head, but I have it. Of course, I mean it will take me a minute, and I'll send it in. I'll send an email about it.
Thank you very much.
Yeah, sure. Yeah, okay. So what's our model? By the way, if you write in the chat, so I can't see it, but maybe if one of you can like tell it, say it to me, and then I'll
Yeah, sure.
and then I'll adjust it. Okay,
Sure.
Okay, so what's our model? Our model is we have an input tape, which is read-only. So notice that we cannot, I mean, if we have an input, we cannot override it with intermediate computation. We have work tape and we have output tape, which we cannot write over. And we measure the space complexity only by the number of cells used on the work tape. Okay, and we say language is in D space f of n if it is accepted by a space-bounded machine with space complexity O of f of n. And the class L is just D space O of log n. And note that we don't have to talk about languages, we can talk about functions. For example, we might want to approximate a function using few bits of auxiliary memory. And that's great as well. We don't have to talk about decision problems. Okay, so this is a deterministic class, but we also want to toss tokens because it helps designing algorithms. So on top of that, we add a random coins tape, but note that it's read-only and unidirectional. So we cannot remember our previous coin tosses. If we want to remember them, we need to store them in the work tape and pay for them. Okay, and same definition, we say language is in BP space f of n if it's accepted by a probabilistic space-bounded machine with bounded, say, error 1/3 and two-sided error. So we have error in deciding if the X is in the language or not in the language. But again, we can talk about approximating a function space efficiently with high probability. Okay, now we need to take the probability over our random coins. Okay, so BPL is BP space O of log n. So these are our two kind of heroes. Okay, so yeah, makes sense to ask what do we know. So Savage's result, although it's not phrased this way, it can be extended to show that BPL is contained in D space log squared n. So this is very classical result. And Nisan's generator, which we'll talk about, but it proves, amongst other things, that we can derandomize BPL in both space log squared n, which was already known, but the same simulation can take polynomial time, which is not inferred by Savage's result. A few years later, Sachs and Zhou brought it down to log to the 3/2 n, and it's been the state of the art for almost 3 decades. And then Hoza managed to shave off square root log n factor, utilizing recent advances in weighted PRGs for branching programs in the low error regime, which I will mention towards the middle end of my talk. So this is what we know about BPL, and again, feel free to stop me anytime.
Oh, sorry, yeah. I just wonder, is the last one a conditional result compared to the first 3?
No. Everything is unconditional. All my talk today will be unconditional. Thank you. Thanks for the question. Okay, but even if you don't care so much about BPL, you might care about the very fundamental problem of matrix powering. So given a W by W real matrix A, we want to compute, or in our case, approximate, A to the power of n. And obviously, it's one of the most fundamental algorithmic primitives, but also it's an important problem in complexity. Specifically, there has been success in better understanding space-bounded computation, both probabilistic and, by the way, quantum computation, through the lens of linear algebra. What we're interested in is the space complexity of approximating A to the n. And it turns out that approximating A to the n for W by W stochastic metrics, where n is polynomial in W, is in some sense complete for BPL, and it's not hard to show. We can convert any BPL Turing machine into a stochastic operator A, such that the probability the Turing machine moves from some state S to a state T can be computed by a to the power of n in indices st. And the other direction is also not hard. You can approximate a to the n st by just taking many random walks from S and counting the fraction of the number of walks from S that reached T. So in a sense, exactly, derandomizing BPL in space O of S is equivalent to approximating stochastic matrix powering deterministically in space O of S. So that's the connection to matrix powering. And there has been many approaches. There have been some approaches to derandomizing BPL, and one of I guess the most successful one is the Pseudorandomness approach. Okay, and I will talk about it now. So what's a PRG? Again, I'm sure you heard about it in Lichi's talk, but let's mention it again for those of you who weren't there. So we have some function class C, curly C, and think about the first scenario where we take some function f from C. It has n inputs, and we feed it with n truly random bits. We call this distribution u of n. So f of un, say it's 1 bit, so it's the output distribution of the function on n truly uniform and independent bits. And let's compare it to the situation where instead of un, we feed a pseudorandom distribution d, which is the output of a deterministic function gen stretching d bits to n bits, where we feed gen with d truly random bits. Okay, and f of d is the output distribution. When we cannot distinguish between f of un and f of d, then we say gen or d fools f. And in general, if G works for any f from the class C, then it's a PRG. So formally, we say gen, a function from d bits to n bits, is a PRG against a function class C if for every f in C, the expectation of f of d is close to the expectation of f of un. Okay, where d is the output distribution of the generator. Okay, so this is a very powerful notion. Notice that the image of gen is very sparse compared to the uniform distribution, which is great. And kind of our motto is that when the adversary, our function class C is bounded, we can kind of explode the structure of the function class. Okay, notice that the bits in D are not independent. They're actually highly correlated, yet the algorithm, because it's bounded, is oblivious to those correlations. And one of the cool things about PRGs is that they give black box derandomization. Why is that? Very shortly, we can just enumerate over all the seeds. More formally, say we have some algorithm with input x and with randomness y. What we can do is replace the random coin tosses with the output of the generator. So given an input x, instead of iterating over all y's, we iterate over all 2 to the d choices of the generator, compute the generator, and use the output as our random coins and take the majority vote. And if d is much, much smaller than the original amount of randomness the algorithm needs, and of course, assuming the PRG is efficient, this saves upon both time and space. And space is our concern now. So in particular, if the PRG runs in linear space, and all of our explicit PRGs run in linear space, then it allows us to deterministically simulate the algorithm in space O of D. Okay. So notice that we think of the input x as being fixed, and we're interested in fooling the function that treats the randomness as the input. And the question is, okay, we want to design a PRG against which curl is C. So just to parallel it to the time-bounded regime, which you may know better, if A is time-bounded, we want our PRG to fool polynomially sized circuits, which is hard. But if A is space-bounded, we can model the way AX acts on its randomness Y as what we call a read-once branching program. So what's a read-once branching program? It computes a function on n bits. So now we treat n as the number of our random coins. We start at, so it's a layered graph. There is, in the first layer, there's just one vertex, and we start with it. We read x1 up to xn in this order, in the what's called a ordered read-once branching program. We transition according to the layered graph, and eventually we end at either accept or reject. And the two quantities to think about is the length of the branching program, in this case n, and the width, which we call W, which bounds the memory the branching program has. And it's not hard to show that for an algorithm A that uses S space and n random bits, if we fix its input, then we just need to fool length n and width 2 to the s read-once branching programs. So in order to derandomize BPL, we need to work against poly n with ROBPs. So this is our model of computation. Yeah, this is, as I said, for BPL. And what's known? So for this case, for the W equals poly n case, in full generality, actually the best explicit PRG is from the 90s with seed length O of log squared n, which is due to Nisan seminal work and the Ajtai-Wigderson generator and follow-up generators. And the question you might ask yourself, so okay, I talked about derandomization of BPL, and then I talked about PRGs, and I showed that PRGs suffice to derandomize BPL. But let's stop and think before we continue. Are they necessary? So we don't know. And the best derandomization results we have are actually not PRGs, but they certainly help. So the best derandomization results use PRGs kind of crucially as a central ingredient. And also Nisan's PRGs and its many variations are suboptimal for the general case, but they are extensively used in various parameter regimes other than the BPL regime for optimal PRGs for different classes. So PRGs are extremely useful. And also resolved by Cheng and Hossa, they show that one-sided error derandomization in what's called a pseudorandomness way, which I won't define formally, would already imply that BPL equals L. Okay, so PRGs certainly help to understand space-bounded derandomization. Okay, and for subclasses, so I mentioned that for BPL equals L, the best PRGs we know have a quadratic log squared n. For subclasses of poly with ROBPs, we do have logarithmic or near logarithmic seed length. So for with 2 and with 3 ROBPs, for certain restrictions of the branching programs, which are called permutation and regular branching programs. We have it also for geometric tests, for example, half spaces. We have it for modular tests, for rectangles, for shapes, for Fourier shapes. I won't get into these definitions. I just want to mention that we do have better PRGs for subclasses of BPL. Okay. Yes, so any questions before I continue? Okay. So the classical approach, but in fact it's used also in recent works, but it's classical because it's since Nisan's PRGs, it's recycling the randomness. What do I mean by that? So the motto here is small width of the branching program means there's bounded communication going on, meaning that upon reaching any vertex, say the red vertex or the middle vertex, if we only know that we reached this vertex, because this is the only thing we need to know in order to complete the walk on the branching program, then the amount of information we have on how we got there is usually at most log W. Okay, or just S, if S is the amount of space the algorithm uses. And we can exploit it, so we can recycle the randomness used to get to the middle vertex using pseudo-randomness primitives, hash functions, expander graphs, what we call randomness extractors. And this is kind of the paradigm, and there are several variations of this stretching d bits to n bits, that full polynomial with ROBPs. Let's just mention just so you can get something concrete out of it, say the INW generator. What we can do is build the INW generator recursively. So we start with just a trivial function, mapping a seed to a seed. And in general, in the ith level, we can take a seed, break it to x and y, where x is longer than y, use x for the previous level, and then take some expander and take the edge xy, meaning that I start with the vertex x, take y as the label in my expander, and then take the second vertex and use it for the previous level of the generator. And this kind of randomness recycling paradigm, if we take it for log n levels, it can be set to output n bits, and one can do the analysis, and it turns out that you need a seed of log squared n. And there are quite several variations of this paradigm, and they all work in different regimes or in the regime of BPL. Okay, but I want to phrase Nisan's generator differently as a randomized matrix powering. So it's a very cool thing. We can take a stochastic matrix and say each entry is represented by S bits, and we have some accuracy epsilon and confidence parameter delta, and we can use Nisan's generator with some randomness h to approximate a to the n with high probability, where the thing is that the length of h, the randomness we use, is pretty long. It's roughly log squared n. Okay? But once we have h written down, the space Nisan's generator uses is very small. It's only logarithmic. Okay, and it's paramount to works that build upon Nisan's generator. Okay, for example, Sachs and Zhou's result, and then later a result by us, which I will talk about.
Sorry, but I only know the extractor through pairwise independent hash functions.
Okay, that's great. That's great. You don't need to know. Sorry, go ahead.
But the extractors also have such properties that as once the extractor is written and everything else is in log space.
Yeah, so there are extractors that satisfy the property that you mentioned, but for this result, you can think about using just pairwise hash functions and not extractors. That's also fine.
I mean, does expanders also have such properties?
Yeah, so the INW generator doesn't, if you use expanders, it doesn't readily give you this result in the slide, but you can do some trick. Some people call it the sampler trick to get this result also if you use expanders. It's pretty technical, but of course feel free to send me an email and I will elaborate on that.
Oh, thank you.
Sure. Okay, great. So that was the recycling randomness paradigm. I want to mention another successful approach, which will not be kind of the main issue in this talk, but it's important to know it because many PRGs are based on it. And it's called the iterated restrictions approach. So we kind of shift gears to a different approach, which is essentially due to Ajtai-Wigderson, and it was revived and crystallized following the works of Gopalan, Meka, Reingold, Trevisan, and Vadhan. And this goes as following. So suppose we want to construct a PRG, and we take some function from our class C, where in our case, C, think of it as just an ROBP. And what we do is pseudo-randomly choose partial assignment to the function. So we have n coordinates, but we hit it with a partial assignment, meaning we leave some of the coordinates untouched, but fix the rest of the coordinates. So star means that we don't fix the coordinate, and otherwise we fix it to either 0 or 1. And we choose this restriction from a distribution over restrictions in a pseudo-random way. Okay, so we hit it with a restriction, and so some of the coordinates remain, but some of the coordinates are fixed. So we have a new function, f prime. And what do we need from this f prime? So we already wasted some bits to compute f prime, because f prime is actually a distribution, because it comes from a distribution over restrictions. But what do we need from this function? We want it to still be contained, of course, in the function class we're trying to follow. We actually, but before that, we also want to the expectation to be roughly preserved, because we want the PRG to approximate the expectation of f, and now we have f prime. So we want the expectation of f prime to be close to the expectation of f. And hopefully f prime is not only in C, but it's actually simpler. We want f prime to be simpler. And in what way? This is actually the progress measure of simpler is a key issue, and you need to design it carefully sometimes. And we continue doing random restrictions, and once f prime is simple enough and easier to fool, we take an off-the-shelf PRG, and hopefully it works. So this is the paradigm, and often for the property that the expectation is preserved under pseudo-random restrictions, we can now use the work by Forbes and Kelly that gives us just that. And also I want to mention that various works utilize the following very interesting phenomena and useful phenomena, that sometimes f prime itself, if we fix the randomness, is not that easy, but the average restriction of f, which we call the bias function, may be similar to full than, as I said, most individual restrictions of f. So it's kind of a thing to keep in mind. And I just want to mention some recent PRGs for space-bounded models that are constructed using this approach. It's not an extensive, exhaustive list. So we have with 3 ROBPs due to Mecca, Reingold, and Tau that use this approach. We have unordered ROBPs, which are actually stronger than ROBPs that I talked about with seed length quadratic, so log to the 3n. And we have near optimal and actually optimal for some parameters PRGs for read-once formulas, constant with read-once formulas that we did with Puya Hatami and William Rosa. Okay, so these were the kind of classical recycling randomness approach and the iterated restrictions approach. Now let's talk about graph algorithms and what we call the Laplacian paradigm, and let's see how it all connects with space-bounded derandomization. Okay, so we can construct PRGs, which is really great. But we can also, to tackle the BPL versus L problem, we can also derandomize canonical problems. And we already mentioned one canonical problem, which is approximating powers of stochastic matrices. And we actually have canonical problems for BPL that go beyond just approximating random walks. And morally, you should think about it as approximate linear algebra on stochastic operators captures the power of BPL. And we have various quantities we wish to study in random walks, in linear system, matrix inverse eigenvalues, and so on. And just if you're interested in quantum computation, approximating linear algebra on Hermitian operators roughly captures the power of BQL. So it's nice to know. This is a side note. So can we derandomize all these linear algebraic quantities in BPL? And of course, we want to do it for arbitrary graphs or arbitrary stochastic operators, but we don't know how to do it in full generality, so it's easier to start with undirected graphs. And some of you may know the seminal, really beautiful result of Reingold, who solved undirected connectivity in L, and it was soon after extended to Eulerian graphs by Reingold, Trevisan, and Vadhan. And this work can be interpreted as understanding random walks in the mixing time regime. So we walk and walk and walk, and either S is connected to T or not. But we want to extend the family of problems we can deal with. So can we approximate other important linear algebraic problems in very small space on undirected or Eulerian graphs? So this would extend the class of problems we can solve space efficiently, but still not the family of graphs we know how to handle. Okay, so this is what we want to do. But first, let's make sure that we are all familiar with what's a Laplacian matrix and what are Laplacian solvers. So we wish to approximate a solution to Lx equals B, where L is the operator D minus A, for A being the adjacency matrix of a graph with the gridded matrix D, and B can be arbitrary. And it's an extremely powerful primitive in the design of faster algorithms for a long list of problems in the time-bounded regime. So you actually want to use it in the space-bounded regime. And note that this really indispensable to the development of the Laplacian solvers is the notion, it's a very useful notion of spectral approximation that began with Spielman, which was later extended in several ways. I won't get into the formal definition of the spectral approximation, and there are several definitions. But yeah, I urge you to look that up. So, in the context of space-bounded derandomization, Murtagh, Reingold, Sitford, and Vadhan gave an algorithm to approximate the solution to Lx equals B when L is undirected with great accuracy, and to approximate powers of undirected graphs, a to the n, where a is where a comes from an undirected graph, but with low accuracy in near logarithmic space. This was later extended due to Ahmadinejad, Kellner, Murtagh, Peebles, Sitford, and Vadhan to the case when L is Eulerian, and this also allowed them to approximate a to the n to within high accuracy, again in near linear space. And kind of the high-level approach of these works is to take inspiration from very clever algorithms from the time-bounded setting and reduce them in a space-efficient manner, often to approximate matrix powers. And to do it space-efficiently, the derandomized squaring operation is used due to Rosenman and Vadhan. And when this reduction takes place, the highly non-trivial part is to use spectral approximation to prove correctness, to show that if we replace high powers with derandomized squaring, the algorithm works. So this is like very, yeah, sorry.
A question.
Hi, Andre.
Yeah, so I somehow forgot the...
Hi, sometimes it's quite, sorry.
Yeah, so for the definition, A is also undirected graph.
No, so in the first result, A is undirected. In the second, you can take A to be any Eulerian graph.
Oh, okay, I see. Thanks.
Yeah. And so it corresponds to doubly stochastic matrix. And again, the stochastic matrix setting is just the general BPL setting. Yeah. So we have this gap. Okay. Good. Okay, so in all these graph-based algorithms, an important ingredient in approximating powers or inverses to within very low error is what's called a preconditioned Richardson iteration. And if you know time-bounded algorithms and even kind of numerical linear algebra or even gradient descent, you may know it because it's like a very heavily used primitive in the time-bounded works, which only now is being used in the space-bounded works. And in recent years, it's been used a lot. And then you can see the list here. And some of the works I'll mention towards the end of the talk. And I want to give kind of the theorem of the Richardson iteration in a way that even those of you who are familiar with the Richardson iteration may not know it in this way. Yeah, so although it's a simple theorem, I think it's a very cool one and worth to know if you don't know it yet. So if we're given matrices A, and think about A as kind of the ground truth, the original matrix, and A1 up to AR, and think about them as approximation to the powers. So we have the guarantee that each AI mildly approximates A to the I. So mildly, by mildly, I mean, say 1 over R, where R is the power that we wish to approximate. Then we have an algorithm, call it Rich for Richardson.
What's the norm?
The norm is any submultiplicative norm. So if you assume something about the norm, then you get the same thing at the end. But it should be submultiplicative.
But there will be a factor of poly W?
Only if you want to move from one norm to another. But if you start with some norm,
yes.
But if you take, but it's fine, because if you start with any submultiplicative norm and you do this error reduction, once k is larger than log w, then you can tolerate this poly w factors, and you can go to any norm that you want.
Thank you.
Yeah, so I'll just mention that once we have these matrices, we have an algorithm which is super space efficient that improves the accuracy of a to the r from 1 over r to r times 2 to the minus k. So it's highly space efficient. Typically, it will run in O tilde of log RW space. Okay. And note that we can kickstart the process. Unfortunately, not when we have like a constant error, but when we have 1 over r error. So you need 1 over r error to kind of kickstart the process. And actually some works, in particular Pine and Vadhan, managed to evade this using more clever techniques for permutations, but yeah, I will not get into it. Okay, and I'll just mention that the Richardson iteration, as I showed you now, is an algorithm. It's not a PRG. But we, together with Cohen, Renard, Sberlo, and Tashma, and also Pine and Vadhan, concurrently, noticed that the Richardson iteration can be made into a black box manner method, but weights must be introduced. And I'll say in a minute what do I mean by weights. And this allows us to take the Nisan generator and reduce the error in Nisan generator in kind of a black box way. So from having seed length, which depends in a bad way on the error, into a seed length that depends optimally in the error. But now it's a weighted PRG. I'll not show why, but I will say what's a weighted PRG. So weighted PRG, it's a very nice notion. It's a black box notion. It's a PRG together with a weight function. So we don't just take the expectation over f of gen of z. We now allow the weights that approximate the expectation of f on the uniform distribution to also be negative. That's the crucial point. The fact that mu is not necessarily 2 to the minus d is not so important. What's important is that mu can be negative. Okay, so using Richardson iteration, we can get better WPRGs that would reduce the error. And this gives an alternative construction to the breakthrough result of Braverman, Cohen, and Garg, who were the first to get low error PRGs for poly with ROBPs. And as I said, it was the Richardson iteration was also adapted to WPRGs for permutation ROBPs due to Pine and Vadhan. Okay, how much time do I have? Okay, that's good. Questions? Okay, this was, I believe, a very quick overview. So again, if you have any questions that go a bit deeper, yeah, of course feel free to shoot me an email. I'd be happy to chat about it. And I want to spend the last 10 minutes discussing recent work with Gil Cohen and Ori Sberlo from Tel Aviv University. And there we considered approximating long random walks. And let's kind of motivate this thing. Okay, so up until now, we talked about the W equals n case. We want to approximate a to the n, where a is W by W matrix. But other settings are also important. we might want to approximate very short or very long random walks and do it better than the general case, or not worse than the general case. We want to de-randomize algorithms that toss few random coins or many random coins, not just n random coins, or not just W random coins. And when we want to distinguish between n and W, what do we know? So to solve it exactly, we need log n times log n W space due to if we wanted to repeat its squaring, or we can actually do a simple algorithm based on the Cayley-Hamilton result, the classical Cayley-Hamilton result, and this would take log n plus log square W. It's actually a nice observation, which I'm not sure written down anywhere, but you can do it with Cayley-Hamilton in this space. Nisan's generator, if you want to distinguish between n and W, this is what it will give you: log n times log n W. And the Saxon-Zhou result is log to the 3/2 n plus square root log n times log W. So if you zoom in and kind of see the dependence on n and on W, this is what you get. Okay, and what do we show? We completely shave off the 3/2 n, well, at the expense of O tilde, but we get O tilde log n plus square root log n log W. So you see that when n is large, this is much better. Okay. So this is the result. And let's be a bit more concrete. So say we fix W and let n grow above W. So say n is 2 to the log W to the C. What's the space needed to approximate a to the n deterministically? So if C is at most 1, both our result and the Saxon-Zhou result gives log to the 3/2 n. By the way, I'll mention that if C is like really tiny, really sub-constant, then this is in the regime of the Nisan-Zuckerman, and there we can get log n, but it's like for really small C's. For C, which is between 1 and 2, our result already improves upon Saxon-Zhou and gives log to the 1/2 plus 1 over C n space. And once you reach C equals 2, you can show that a Cayley-Hamilton based algorithm can give you log n. So you see the interpolation between log n and log to the 3/2 n space. And of course, because we know the connection between approximating pairs of stochastic matrices and derandomizing space-bounded algorithms, we can readily apply our result to derandomization of algorithms that toss many coins, because n here is larger than W. Okay, any questions about the phrasing of the result? Okay. So what do we use? We actually use the two. So we used Richardson Iteration, which I talked about now. We use Nisan's generator, and we extend upon the Saxon-Zhou's approach, which itself uses Nisan's generator, together with a very cool shift and truncate technique in order to recycle the randomness in Nisan's generator. So I won't have time to go into many details, but I will show some details in the time that I have. So the Saxon-Zhou algorithm, what it does, it applies Nisan's generator many times for square root log n times. So if we fix r to be 2 to the square root log n, and you take a to the r R times, then you get A to the N. So it's a very natural idea to try, but the question is for which randomness Nisan's generator to use, right? We have R applications of Nisan's generator. And of course you can think about taking independent HIs, but it's way too costly. And you can think about doing the same H across all iterations, but this shouldn't work because there is an adaptivity issue. Once you apply Nisan, the next matrix that you need to take to the power of R, it may heavily depend on the previous H that you used. So it's an adaptivity issue, and future iterations may fail miserably. But Sachs and Zhou noticed that a good application should not heavily depend on H, and they used a very clever shift and truncate technique. I'll just put the, I don't really care about the parameters now. I'll just put their algorithms. So what they do is that they apply Nisan generator, and between consecutive application, they shift each entry of the matrix by a random shift, and then truncate the result. And the nice thing here is that with high probability over the shifts, the truncated matrix will be equal to some canonical matrix that doesn't depend on H itself, so we can kind of keep using the same H. So we pay for the randomness in the shifts, which is already log to the 3/2 n, and we pay for the space complexity of Nisan's generator, which is also amounts to log to the 3/2n. And there are two bottlenecks in the construction. Sorry for going over it quickly, but again, send me an email if you wish to discuss in detail. So there are two bottlenecks. The first one is the magnitude of the shifts, which is already log to the 3/2 n. And the second one is that this generator is costly if the input matrix is represented using many bits of precision. And it's actually essential. If we want to raise to the power of n, we need 1/poly n accuracy, we need log n bits of precision, but it's costly. Okay. And we overcome these two bottlenecks. As I said, we do need to meet an accuracy of 1/n. And we overcome these two bottlenecks. So let's forget about the first bottleneck. The strategy for the second bottleneck is before we apply Nisan's generator, we purposely decrease the precision of the input matrix by truncating its entries, and we apply Nisan's generator with low accuracy. It seems strange. Now this would require a good seed. It seems strange because mild approximation at each iteration is not enough. We want to we need high precision. So what we do is we retrieve the high precision using Richardson iteration. So I have just 1 minute, and I want to show you kind of the outline of the construction. So what we do is we truncate the matrix, we apply Nisan, we retrieve the original accuracy using Richardson, and kind of we tweak it a bit. We do shift and truncate, and then repeat the process. Okay, of course, it's delicate because everything should be done space efficiently. We never store entire matrices in our memory. That cannot be done. But this is kind of the general scheme. And I'll just put down the known results and our results. And thank you. If you have any questions, feel free to ask.